Hoover High School AP Chemistry. This is the answers video for your assignment day 59, lesson 34 on covalent molecules and how to create, use Lewis structures to create covalently bonded molecules. So this was assigned on Monday. It's due on Friday, although try to get it done by Wednesday because we're going to start a new topic, and it's a pretty extensive topic on Wednesday, and we don't have a lot of time to cover it. So get this done. It's a pretty quick and simple assignment. All right, so let's go ahead, and this is just a review of what you did in the foundations unit. It's drawing some Lewis dot structures of some basic elements. So the whole principle is that the Lewis dot structure involves only the letter, this atomic symbol of the element, and then the valence electrons, and they're drawn in a certain way. So first of all, let's find this element fluorine, and it's in the second row, and it's 1, 2, 3, 4, 5, 6, 7 elements from the left. It means it's going to have 7 valence electrons. Now the way you want to draw those is you want to start off spreading those electrons out so that they're 4 separate electrons. It doesn't matter whether you start top, bottom, or sides. I usually start at the bottom, on the bottom right. So we'll do that, and I don't always do that, but I usually do that. So there's one, there's a second one, there's a second one, or third one rather, and there's a fourth one. Okay, so those are 4 unpaired electrons, but we need to place 7. So now we start pairing them up, starting with the 5th electron, the 6th, and the 7th. Okay, and what you see that fluorine has in its natural atomic state before it's bonded is it has a single lone electron, a single unpaired electron. So that's where another element could come in and share an electron, or where fluorine, which is the most electronegative element, could actually take an electron away from, say, a metal, alkali metal, alkaline earth metal, or transition metal, and pull it in to create an ionic bond. But anyway, this is the only, if you want to circle that just to emphasize that that spot is empty. These are paired electrons, so they could only bond in certain situations, which we'll talk about later. Okay, so that's the diagram. That's all there is to it. Aluminum. We look down here, and aluminum is the third element from the left in the third row, 1, 2, 3. So it's going to have 3 valence electrons, 1, 2, 3. So it has 3 places where it can bond. And as you may remember from the earlier lesson, that aluminum will only have 6 valence electrons when it's full. When it doesn't create an octet of 8, it only creates an octet of 6. It's an exception to the octet rule. Okay, let's take selenium. This is an interesting one because it's down here in the 4th row. And there it is right there. So how many valence electrons does it have? And that brings up the question, do all of these transition metal elements in here count as valence electrons? The answer is no. Only what are called, and I haven't introduced you to this term, but I will, and I'll introduce it to you now, the representative elements, which are the first 2 columns and the last 6 columns, basically this block in here. Those are the only ones that form valence electrons, or that provide valence electrons, those. These, they have valence electrons, but the additional electrons that they get in this orbital, we're going to talk about the structure of this orbital. It's a little more complicated than we've talked about so far. Where does this orbital come in compared to these, which seem to have a nice orbital with 8 electrons? What about down here? A little more complicated down here. We'll deal with that after the next break. But for right now, what you just simply have to understand is the valence electrons are the same as the first 3 rows, or the same as the second and third row, I should say. It's 1, 2, 3, 4, 5, 6. So it's the 6th element over. So it's going to have the same valence electron configuration as oxygen or sulfur. Okay, so let's just go ahead and draw that. And 1, 2, 3, 4, and then you start pairing 5 and 6. So it's exactly the same electron configuration. Therefore, it forms similar compounds to oxygen and sulfur. Okay, iodine is pretty straightforward. I'll let you do that one. Magnesium is a 2+. Okay, so now we're dealing with a magnesium 2+, and magnesium is right here, and normally it would have 1, 2 valence electrons, but a 2+ means it's lost those 2 valence electrons, so it now has the electron configuration of neon. So it now has a full octet. Because it lost those 2 electrons, it's also lost that 3rd orbital. So now it's going to look like this. The way you would write it is like this. You're going to write it with a full octet because it now has the electron configuration of a noble gas, and then write the 2+ right there. Okay, so that wasn't shown to you in the instruction videos. All right, let's do chlorine, same thing. Okay, chlorine is 1 electron away from becoming argon, so it wants to gain an electron to become like argon, so it's also going to have a full octet. And I drew that on the wrong side, but it's okay because we're going to end up filling the octet anyway. Doesn't matter. Okay, there you go. And then you write the 1-, or you could just write minus. So that's a chlorine ion, chlorine anion. Okay, so you go ahead and do oxygen, all right? And it's done the same way as those. All right, now we're going to draw some Lewis structures here. And we did this one in the video, but let's follow the rules. So determine the total number of valence electrons. So I want you to write this out. I don't want you to just draw the structure. I want you to show me the calculations that you got for that. So for hydrogen, we have H. Okay, we have 2 of those, and each one has 1 valence electron. E- means electron, so that's a total of 2. And we have oxygen, has 1. There's 1 oxygen. Each one has 6 valence electrons. So that's a total of 6. Minus. And now you add those and you get 8 minus. Okay. The next rule says draw the structure, least electronegative element in the middle. That would be hydrogen, but it can't be a central atom because rule B, 2b says hydrogen and fluorine can only occupy terminal positions. So I'm going to draw it like this. I'm going to put oxygen as the central atom. Even though it's higher electronegativity than hydrogen, hydrogen could only form 1 bond in 1 location, so it cannot be central to more than 1 atom. It can't be central at all, in other words. All right, connect the outside atoms with the central, so we do that. Okay, so now we've used 1, 2, 3, 4 of our 8 electrons that we need to use. Create octets for all terminal atoms. That's already done. Hydrogen can only hold 2 electrons. It's in the first row. First row is 2 electrons, so it does have a full octet. 5, assign remaining electrons as lone pairs to the central atom, so that would be oxygen, so we'll just go ahead and create a full octet there, or lone pairs. All right, and form multiple bonds if necessary. Well, let's see. We've used our 8 electrons. Everyone has an octet. Hydrogen has 2 electrons, and oxygen has 8 that it needs. So this is done. This is the complete diagram. As I mentioned in the video, this is not the geometry of a water molecule. It is not a straight linear molecule. We'll talk about geometry when we return from the break. Okay, CO2 was also done in the instruction video, so watch the instruction video to see how CO2 is formed. CH4. So let's follow the rules. So you should have these rules in front of you. If you don't, I would like you to copy them down so that you have them in front of you. And then you'll be able to do these. So CH4, the first thing we're going to do is determine the total number of valence electrons. So there's 1 carbon. It has 4 valence electrons. And there's hydrogen. There are 4 of those, and each one has 1 valence electron. So the 2 of them together contribute a total of 8 valence electrons. All right, now we come over here, we draw the structure, least electronegative. Again, the rule you really have to follow is that hydrogen cannot be the central atom. That means carbon must be the central atom, so we're going to draw it like this. And there's 4 of them. So for lack of any better information, we're just going to assume they go around symmetrically like that. And we're not too concerned with geometry at this point and where they actually lie. So we're going to just draw them like that. All right, connect the outside atoms with the center using single bonds. So there we go. There's a single bond there, there, and there. Okay, remember what our objective is. We're trying to use all of the valence electrons that we have. We have to use all 8. We have to end up with exactly 8 dots in this diagram. And everyone has to have an octet. Well, we've used the 8 dots, and everyone has an octet. Hydrogens do, and the carbon does. Therefore, this is complete. We don't need to go any further on the list of rules. That's it. And that actually is the structure, somewhat the structure of methane. It's actually a, we'll find out when we get into geometry anyway. Okay, NO2, let's do that. So nitrogen. There's one nitrogen, it has 5 electrons. Okay, now this is a tricky situation because we have an odd number of electrons. Whenever you have that, something usually funny is going to happen with the octet rule. So let's just go ahead and discuss that one. So what often happens with a covalent compound when there's an odd number is you're not going to be able to create octets for everything. So oftentimes it wants to draw in an extra electron. So I'm going to change this to a nitrate. It's called the nitrate ion. I'm going to change it to a minus. That's a 1 minus, okay? That's going to give it an extra electron here. Now again, there are exceptions to the octet rule, but this generally will want to draw in an extra ion. So I'm actually going to change this to an E minus, and there's one of those times an E minus, and that's going to equal an E minus. And so what you're going to have here is 18. All right. So you say, well, how did you know to do that, or how do you know when that happens? Well, generally, I should have first started. I think I should have given it to you simply as an NO2 minus. But in this case, it will be given to you generally. You won't have to figure those out. All right. So let's go ahead and do this. I know in the AP, I don't believe they've ever asked one that was like this. It's usually been a nice number that will create octets. Okay. So here we go. NO2. So the least electronegative of those, if you go to the periodic table, again, you can use the periodic table of electronegativities, or if you know your periodic table rules, the highest electronegativity is fluorine. They increase as you go from left to right. So oxygen is more electronegative than nitrogen. So that means nitrogen, according to the rule, is going to go in the middle. So let's draw the structure here. Okay, and we'll put nitrogen in the middle. So it says determine the total number of valence electrons. We did that. Least electronegative occupies the center. We just did that with nitrogen. And so down number 3, connect the outside atoms to the central atom using single bonds. So there's a single bond. There's a single bond. So now we've used 4 of the 18 electrons. The next rule says connect the outside atoms to the center. Create octets for the terminal atoms. Now you should not be doing this in ink because you were always, even by design, you're going to be erasing electrons and rearranging them. So don't do this in pen, okay? But we're going to create octets for these 2 oxygen atoms out here. Okay, and now we're going to count. We have 8 there and 8 there. We need 2 more. Okay, so where are we going to get those 2 more? And so 2 things. We need to have 18. We only have 16. And nitrogen doesn't have an octet. So that means we need to add 2 more. So the place where I would add those 2 more is right here, because I need to give nitrogen 4 more electrons anyway. So now nitrogen still doesn't have an octet, but now we have the correct number of electrons at 18. So where do you get the other 2 from? Well, you get them from one of the lone pairs. You rearrange it. We don't want to add or subtract any more electrons because we have 18. But nitrogen still needs 2 more. So we get it from one of these lone pairs out here. So I am going to pick this one. And now where do I put it? Well, I can't put it here because once I added those 2 electrons and I still had those there, I ended up having 10 electrons around this oxygen. So it can't go there, and it can't go here because that already has 8. So it's going to have to be a lone pair up here that doesn't attach to the oxygens. So again, be sure that our rules have been obeyed. 18 electrons, you can count them. There's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oxygen has an octet, nitrogen has an octet, and this oxygen has an octet. So that is the final configuration. Now you'll notice this is a, well anyway, you'll notice one thing, and we're going to talk about this later. Why did this double bond go on this side? Couldn't I have done that over here and moved this pair in? You could have. We're going to talk about what that is called and how you deal with that in the next lesson. Okay, let's keep going. All right, let's go to G, H2O2. All right, so first rules, we're going to figure out how many electrons there are there. And there's 2 hydrogen. And 2 oxygen. And each oxygen has 6 electrons. And that's a total of 14. Okay, so you have 2 hydrogen, 2 oxygen. The hydrogens cannot be in the middle of the oxygens because they can only bond on one side. They only have one hand, so they can only hold hands on one side. They can't hold hands to two different elements there. So we're going to have to draw this like this. Okay, again, you can't have a hydrogen in there. All right, and the next thing we're going to do is connect atoms with central atom using single bonds. Well, there's 2 central atoms, but we're basically going to just connect everybody with single bonds here, like that. All right, so we've used 6 of our 14 electrons. Now we're going to fill the outside elements with octets, but hydrogen and hydrogen already have a full octet with 2 electrons. So now what we're going to do is we're going to assign the remaining electrons as lone pairs around the central atom. And so we have 8 to deal with. So there's 1, 2, 3, 4, 5, 6, 7, 8. And form multiple bonds if necessary. Well, let's see if that's necessary. We've used 14 electrons. We had 14 to use, so we passed the first test. The second test is, does everyone have an octet? The answer is yes. Every element here has an octet, so this is your final answer. Again, this doesn't tell you what the geometry of that molecule is, whether it's bent somewhere, but we will learn that later. Okay, I'm going to skip to I. I'm going to let you do H, so that's for you to do by yourself. That's one that I will check. And let's go ahead and do I. So carbon, 2 carbon, each one has 4 electrons. And then you have 4 hydrogen. And each one has 1 electron. Again, we're just looking at the periodic table and seeing how many elements from the left each of these elements are. Okay, so that's 4. Add that, you get 12 electrons. Okay, again, hydrogen cannot be a central atom, so carbon must be, the 2 central atoms must be carbon. And for lack of knowing where to place the hydrogens exactly, we can just place them symmetrically in some fashion. So since there's 4, I'm going to put 1 here, 1 here, 1 here, and 1 here. That's pretty symmetrical, okay? You could have drawn them kind of at diagonals. I would recommend you don't do that. Don't worry about geometry when you're doing this. Just kind of do what seems like the simplest structure that seems symmetrical in this case. Okay, next thing is we are going to connect outside atoms with central atoms using single bonds. You're also going to connect the 2 central atoms with a single bond. So I'm going to put a single bond here. Okay, everybody has single bonds. And what do we do? How many electrons do we use? We used 6, 8, 10. 10 electrons have been used. We need 2 more. And we see that the hydrogens all have full octets with 2 electrons. This carbon only has 6, and this carbon only has 6. So what can we do? We need 2 more, and we need to create an octet for carbon. So that's a pretty easy one. You just stick it right here in the middle. It creates a double bond for the 2 carbons. So we've now used 12 electrons, and everyone has a full octet. So this is our final structure for this molecule. Okay, HCN was done on the video, so the only one I'm really leaving you to do by yourself. So with CO2, the only one I'm really leaving you to do by yourself is H. Okay, here's some questions that are straight off the video and the notes. Remember, I'm including the notes as something I want you to review. The notes are largely review, but there is some new material in there. So one of the things that is review is what's a unit cell. That's not in the video. It's in the notes. I'm just going to write that here. And the reason is simply I want you to compare a unit cell with a molecule. What's the difference between the two? And that's actually the question I ask you right here. Okay, octet rule is very basic. Okay, we've said that 1,000 times. That's in both the video and the notes. Okay, this is notes only. There's 5 different ways you can draw molecules. And go ahead, it's just different, they're different structures. There's the space-filling model, there's the perspective model, and there's 3 others. So go ahead and draw just an example of those. You can just use a simple molecule like water or methane, okay, CH4 if you'd like. Okay, write the formula for computing the formal charge. That's in the notes and in the video. It's in the video as well. Give 3 reasons for exceptions to the octet rule. That's in the notes only. I gave you one of those in the video, but the other 2 are in the notes only. One of them you won't understand about extended octet until we get to the unit after the Christmas winter break. What is the relationship between number of bonds, single, double, triple, and both bond enthalpy and bond length? So bond enthalpy is defined in the notes, so I'm going to say this is an answer that you need to go to the notes for, but that is in the notes. What is bond enthalpy? I should have asked that first probably, but anyway, that's in the notes. What is dipole moment? That's only in the notes. Okay, and this was in the video and is in the notes. So go ahead and what is the range of electronegativities to create the 3 different types of bonds, polar or ionic bonds? That's in the video and the notes. And then I just give you an exercise to identify whether each of these is ionic, polar covalent, or covalent. So let's do a couple of them. I'll do a couple of them for you here. So A, first of all, I want you to write down what the electronegativities are. Okay, so here's the periodic table of electronegativities. You should pull this up while you're doing this. If you have a binder, this will be in the reference sheets in the binder that you have. And so we're dealing with A, we're dealing with carbon. So write down what its electronegativity is. And for carbon, it's 2.5, that's C. And for bromine, Br. You see it over on the right, fourth row, and it's 2.8. So 2.8 minus 2.5. You always want to subtract so you get a positive number. That's going to equal 0.3. Okay, so I've written that down here. 2.8 for carbon, bromine's 2.5 for carbon, bromine's 2.8. Subtract, you get 0.3. And according to the table, okay, so here's the table that's in the video. Now you'll notice, honestly, that the table in the notes is different. It's got slightly different numbers, a 1.8. I changed one without changing the other. The fact is, there's no firm number for these dividers. These are very rough. Different books will show you different numbers. I rounded it up to 2.0, but in your notes it shows this as being 1.8. In this case, it's not going to matter. The covalent bond is anything less than 0.4, and that's where we are with this particular combination of carbon and bromine, so it's going to be a covalent bond. Okay, so there you see 0.3 is going to be a covalent bond. So you should have that table in front of you as I'm speaking right now. Again, these things should all be in front of you. Let's try potassium and oxygen over here. So potassium. Okay, and we will pull up the periodic table of electronegativity. So potassium is a very low electronegativity, 0.8. It does not pull in electrons at all. Oxygen is relatively high, 3.5. So we will come back over here, and it's going to be 0.8 and 3.5. Okay, so again, we're doing this one. So that's going to be 2.7. So that's going to be ionic. That's definitely above either 1.8 or 2, whichever table you use. And that's going to be an ionic bond. And I should have written this one is going to be covalent, not polar covalent. Okay, and this is C right here. Okay, so there I've done 2 of them. You do the rest of them. Use those 2 tables, and that will do it. Okay, that takes care of this lesson, and we'll go on to a formal charge and resonance on the next lesson.